Is visible
Yes, sir.
Yes,
and I am clear audible, na?
Yes, sir.
Okay. So yesterday we were discussing analogy. So what is basically this analogy is already we have established our understanding that heat transfer is similar to mass transfer is similar to fluid mechanics or momentum transfer. This understanding we have already established using say laws, okay, laws and fundamental parameters associated with laws like Newton's law of viscosity, then Fourier law of heat conduction, then Fick's law of diffusion, and then Newton's law of cooling, and then we have Heining equation, and then we have Slattery equation. Likewise, we have established our understanding that now heat transfer is similar to mass transfer is similar to momentum transfer. Now these analogies is part of that understanding only, but here we are one step ahead in that understanding. Now for limiting cases, for some limiting cases, for say you can establish a relation between these three areas. So first analogy we have discussed was Reynolds analogy. So this is generalized analogy. This is generalized analogy true for uh, any situation, but here actually this delta mass transfer boundary layer thickness, heat transfer boundary layer thickness, and this momentum boundary layer thickness is theoretically defined, theoretically introduced quantity to catch the theory of an experiment. Okay, so it doesn't have actually you cannot measure this as such. So people have tried to eliminate this with some assumption and observation. Assumption and observation. So this is what Reynolds has done first. So he has assumed, okay, he has observed that for gaseous flow, when gases is associated with that, these three boundary layer thickness are same. Thickness of all three boundary layer are same, and then friction factor. Okay, friction factor. Then if these three are same, this is you can say a first view of Reynolds boundary Reynolds analogy. And moreover, for gases, this Prandtl number equals to Schmidt number. Order of magnitude will be close to one. Okay, will be close to one. So this is the Reynolds analogy. F by 2 equals to Stanton number for heat transfer equals to Stanton number for mass transfer, which is known as the Reynolds analogy. And certainly, this is all good for the whatever experimental limitation of experimental observation what Reynolds has given this analogy. So all the properties are estimated at average temperature, and this is valid for only gases. Okay, then Chilton Colburn added. Okay, Chilton Colburn added. So he observed that delta by delta t for wide range of Prandtl number and Schmidt number, delta by delta t equals to Prandtl number raised to 1 by 3. Okay, they have somehow related this delta t and delta c by measurable quantity. Now Prandtl number can be easily measured, so they have related this. Okay, so delta by delta t equals to Prandtl number raised to 1 by 3, delta by delta c equals to Schmidt number raised to 1 by 3. So he has given JH factor. This is Colburn J factor, which is called Colburn J factor for heat transfer and mass transfer. So limitation, again, all the properties are estimated at average temperature. So there will be say limiting value of temperature. This is bulk temperature. This is what temperature. So property are estimated at average temperature. Moreover, this Prandtl number, this analogy is valid from Prandtl number 0.6 to 60 and Schmidt number 0.6 to 3000. So certainly this analogy is true wherever this Reynolds analogy is true. Reynolds analogy is true for Prandtl number 1, Schmidt number 1. This Prandtl number 1 is included, Schmidt number 1 is also included. So same analogy is true for all wherever you can apply Reynolds analogy, you can apply Chilton Colburn analogy. So, but if delta by delta c is not equals to 1, okay, delta by delta c is not equals to 1, okay, so certainly there will be variation. Some variation will be there from the result of Chilton Colburn analogy and Reynolds analogy. But most widely used analogy is the Chilton Colburn analogy. It is very easy and widely applicable in various problems. Actually, this Chilton Colburn analogy, because it is including all this limitation, as well as Chilton Coleman discussed the geometric limitations. Okay, this is called as a geometric limitation of Reynolds Chilton Coleman analogy. Geometric limitation, say flow over flat plate, where you can have F by 2 equals to JH equals to JM, and flow over cylinder. Okay, flow over cylinder, JH equals to JM, but it is not equals to F by 2. Okay, because mass transfer, surface area for mass transfer equals to surface area for heat transfer, but surface area to momentum transfer is not same. Okay, so this already we have discussed yesterday, so maybe in next figure. Similarly, flow over sphere. Okay, flow over sphere, so it will be actually GH equals to JM, and this is flow in the pipe. Flow through pipe, when flow through pipe, F by 2 equals to JH equals to JM. So that will be equals to, that is true only for Reynolds number greater than 10,000. All this limitation, there is no theoretical background for this limitation. Why it is for Reynolds number greater than 10,000 only? Why? So this is, there is no limitation. There is no, because Chilton Coleman analogy try their level best to fit this equation for experimental observation, and they observe that for Reynolds number greater than 10,000, it is fitting very well. It is fitting very well, and that will give the limitation for Chilton Coleman analogy for flow through pipe if Reynolds number is greater than 10,000. So this, why here F by 2 equals to JH equals to JM, here F by 2 equals to JH equals to JM, and here JH equals to JM, here JH equals to JM, but it is not equals to F by 2. Why it is so? Because of this. Okay, you can say this is the example flow over flat plate. So this is the first example, flow over flat plate. So here you can see, so while calculating shear stress is nothing but a momentum flux. This total area, width into length, is taken into account for calculating shear stress. Okay, so it will be force per unit area. Area will be a length divided by width. Okay, similarly for calculating heat flux, again same area. Area is same. Mass flux also area is same. But on other case, if you are taking a curved surface, and this is the flow over curved surface, take an example of flow over sphere. So, sir, what is the surface area taken for estimation of momentum flux or shear stress? It will be projected surface area. Okay, it will be projected surface area. So for flow over sphere, the area which is taken for shear stress is nothing but pi r square. Okay, it will be projected surface area. It will not be a, you can say, surface area of a sphere. It will be pi r square. That will be projected surface area of a sphere. This is clear to everybody? This is clear to everybody? Here, roll number 6, Aksh single.
Yes, sir.
Yeah. Yesterday, if you remember, I have given one more example where for calculating shear stress, generally projected, how projected area is used. What is that example, if you remember?
Sir, I don't remember the example exactly.
Okay, but yesterday I told, and that you have covered in, say, equipment design. In equipment design, while calculating the shear stress exerted by wind, on tall vertical vessels, what is the area you have considered? It is not twice pi RL. What is the area you have considered? It will be diameter into length. Because
yes, sir. Area of rectangle we will consider.
Yeah, rectangle. Why rectangle we will consider? Because this direction of pressure, okay, pressure force will not be perpendicular all the surface area. So this is what example is given, but you need to consider a perpendicular direction pressure. Okay, for calculating shear stress, so pressure perpendicular to surface. So now wind is flowing in this direction. So perpendicular, this will be this is the perpendicular direction, this is the perpendicular direction, but calculating shear stress, you are calculating perpendicular pressure to this surface. So it will be consist of this component and this component, which will be taken from this wind velocity. Similarly here also, this is the wind velocity, and pressure force is perpendicular, pressure force consider which is perpendicular to this actually, and that is calculated for shear stress. It is shear stress, not tensile stress, shear stress. So same logic here also. That is why this f by 2 is not equals to j, is not equals to jm if for flow over cylinder and flow over sphere or flow over curved surface. Okay, for flow over curved surface, jh equals to jm. For flow over sphere, jh equals to jm, because a surface area for momentum transfer is not same as that of surface area for heat transfer. But for every case, surface area for heat transfer and mass transfer are same available surface area. Okay, so that is what. So using any analogy is as important as knowing the limitations of that analogy. You should not use any analogy blindly. And we are considering for discussion only two analogy in a class. Okay, in a class we are considering only Reynolds analogy and Chilton-Colburn analogy, but there are thousands of analogy available in a literature. Thousands, I am telling. Almost every year, some 10-15 analogies will be published. If you are very much interested, you can go in literature, you will find so many analogies. Almost you can also give your analogy, because everything is starting with basic fundamental equation and discussing how this heat transfer boundary layer thickness, mass transfer boundary layer thickness, and momentum transfer boundary layer can be interpreted in terms of measurable quantity. That is what the analogy is there. So that you will put in some measurable form actually, an observation based on experimental observation. So you can give analogy, a corresponding analogy. So likewise, there are so many analogies, but Chilton-Colburn analogy is a widely used analogy in chemical engineering. As far as chemical engineering is concerned, as far as engineering is concerned, Chilton-Colburn analogy is widely used and adopted for most of the cases, because it covers a wide range. First of all, it covers a Prandtl number from 0.6 to 60, Schmidt number from 0.6 to 3000, and it covers the geometric limitations also. It has explained geometric limitation, and so almost you can say 80% of your problem can be solved using Chilton-Colburn analogy within, say, physical limitations of parameters in most of the engineering problem. So that is why the Chilton-Colburn analogy is widely used mm, in many cases. Okay, so this is the limitations actually. So anybody has any doubt in Reynolds analogy and Chilton-Colburn analogy? Any confusion? Okay. Now today we will solve the problem actually. This is the problem based on analogy. Okay. Based on analogy, this is the problem. So take down all the given data. So now whenever you want to solve any problem, so read the problem carefully and take out all the given data in standard nomenclature, like pressure, capital P, temperature, capital T. Temperature is in degree Celsius, convert that in Kelvin. Then velocity, capital V, okay, 15 meter per second. Heat transfer measure indicates, again, at this given temperature, average heat transfer coefficient is given, H equals to 21, V infinity raised to 0.6. Okay, then what is given is use Chilton-Colburn analogy. It is given, use Chilton-Colburn analogy. Even if it is not given here, apply Chilton-Colburn analogy. This hint is given. Prandtl number is 0.7. Okay, Prandtl number is 0.7. So you need to use the Chilton-Colburn analogy. So that is what here you can apply Reynolds analogy also, but here it is given use Chilton-Colburn analogy. So we use Chilton-Colburn analogy. Then saturated pressure is given, saturated water. Okay, saturated pressure for water at 350 degrees Celsius and 308 Kelvin. Yeah, 35 degrees Celsius, 300.56 bar. Okay, so you convert this in atmosphere or you convert this in atmosphere bar. Then the density is given. You better convert this in bar because this bar SI unit is given. So new kinematic viscosity is given. So 16.47 into minus 6 meter square per second. CP is given, Prandtl number is given, and diffusion coefficient of water in air is given. So it is 2.88 into 10 raised to minus 5 meter square per second. So DAB is given. So nu is given. So what is there? Estimate the mass transfer coefficient. So how to get mass transfer coefficient then? Roll number 22.
Hello?
Yeah, how to get mass transfer? What is that Stanton number for mass transfer?
Uh,
What is that Stanton number for mass transfer?
sir, it's
What is Chilton-Coleman analogy? This is very pathetic situation actually. So you need to get this Kc and then you need to get this CaW, then you can get rate of mass transfer. What is Ca infinity? Ca infinity is assumed to be a zero, almost zero. So how to get CaW? Roll number 22. Yeah, Raman. What is Raman or what? Roll number 22.
hello? Sir,
How to get CaW?
sir, saturation pressure by R.
Okay. P sat divided by R.
RT, sir.
RT. How to get this mass transfer coefficient? Using Chilton-Colburn analogy. You use Chilton-Colburn analogy. So Stanton number into Prandtl number. What is Chilton-Colburn analogy? So Chilton-Colburn analogy, you can see this is the Chilton-Colburn analogy. Stanton number for heat transfer into Prandtl number raised to 2 by 3. That is equal to Stanton number for mass transfer into Schmidt number raised to 2 by 3. So Prandtl number is given. Stanton number for mass transfer. What is Stanton number for heat transfer? Here, roll number 33. What is Stanton number for heat transfer? Vikram. Roll number 58. Devang.
Yes, sir.
What is Stanton number for heat transfer?
Sir, it is H upon rho Cp into VCH.
Very good. So velocity is given.
Yes, sir.
So rho is given. Cp is given. So you can calculate H also using velocity. That relation is given. What is Prandtl number is given. Okay. What is Stanton number for mass transfer? Devang.
Sir, it is Kc upon VCH.
Okay. So only if this JH equals to JM, only unknown is Kc. Isn't it? Devang? Okay. And then Schmidt number. Okay. So how to get Schmidt number then? Schmidt number? Yeah, roll number.
Schmidt number
Yeah, Devang. Tell me, Devang.
V upon DAB. Like Yes, sir. V upon DAB.
Okay, so that schemate number also I can get. So only unknown in JM equals to KC is unknown. So you can estimate the value of KC. If this equals to this, okay, this is flow or flat plate. So JH equals to JM. So in fact, you can estimate friction factor also. JH equals to JM. So you use this JH equals to JM. Or everything is unknown. Known only unknown is, you can say unknown is this KC. Okay. So there you need a diffusivity actually. Diffusivity at given at 313 Kelvin. I want a diffusivity at 308 Kelvin. So this is given at 313 Kelvin. So get the value of diffusivity at 308 Kelvin. This will be needed for estimation of schemate number. Okay, schemate number. Get the diffusivity. So what is the diffusivity at 308 Kelvin? Roll number 74. Nikita.
Hello, sir.
Yeah,
Am I
diffusivity.
audible?
Yeah. Diffusivity at 308 Kelvin.
Uh, Diffusivity at 308 Kelvin is 2.88 into 10 to the power minus 5 meter square per second.
Okay. So this 308 Kelvin is 2.81.
Yes, sir. 2.81 into 10 to the power minus 5 meter square per second.
Okay. Then next is get the value of schemate number. What is schemate number? Roll number 83. Ishwari.
Sir, schematic number is 0.5, sir. 0.58.
Okay. What is the formula for schemate number?
Sir, V by DAB, sir.
Okay. DAB at 308 Kelvin. Okay.
Yes, sir.
Okay. And what is V?
Sir, V is velocity, sir.
So bulk velocity is given. Okay, bulk velocity is
Yes.
given. So bulk velocity is given. So you can use this JH equals to JM. For this, I need a schemate number. So calculate the schemate number. So this is Stanton number for heat transfer. You can see heat transfer coefficient is given, density is given, Cp is given, velocity is given. Similarly, Stanton number for mass transfer. This is not given, velocity is given, Prandtl number is given, and only schemate number is unknown. So that can be estimated, nu by DAB. It is not V by DAB, it is nu by DAB. What is this actually? Hey, Ishwari?
Sir, mu by DAB, sir.
Not mu, nu.
Nu.
What is nu equals to? What is this nu? This is velocity, Ishwari.
Yes, sir, velocity.
This is velocity. What is the physical significance of schemate number? Roll
Sir,
number.
it tells,
Yeah, it is. Ishwari.
sir, it tells the mass transfer and also momentum transfer.
So V is representing this momentum transfer. Okay, what is the unit of DAB?
A meter per second, sir.
Okay, okay, that is also true. But nu is not a velocity. Nu is a kinematic viscosity.
Okay, sir.
You go back and revise your schemate number actually. So this was only second dimensional number we have discussed, which is explaining the ratio of momentum transfer coefficient to mass transfer coefficient, not moment. This momentum diffusivity to mass diffusivity. Okay, momentum diffusivity to mass diffusivity. Momentum diffusivity is nothing but kinematic viscosity, which is given. Kinematic viscosity, what is the value of kinematic viscosity given? Given is, you can see this kinematic viscosity is 16.47, okay, at 308 Kelvin. So you have estimated DAB. So what is the value of schemate number, Ishwari, then?
Sir, 0.586.
0. Okay, you
58.
okay. So now using this relation, you can get the heat transfer coefficient. Substitute this, okay, Schmidt number here. So you can get mass transfer coefficient. Okay. So what is the value of mass transfer coefficient? Roll number 109, Sashank.
Yes, sir.
What is the value of mass transfer? First of all, get the Schmidt number. What is the value of Schmidt number?
Schmidt number value is 0.586, sir.
Okay, Prandtl number is given, velocity is given, rho is given, Cp is given, so you can get a mass transfer coefficient. So what is the
Yes, sir,
value of?
calculating. Yes, sir, calculating. 21 into.
This is the you can say correlation given, which is where we are correlating heat transfer coefficient with the velocity. This is given. Now here in this problem, you can see all the data is given in mass transfer, kind of in mass transfer, and only diffusivity is given. So using this diffusivity, I can get mass transfer coefficient. Heat transfer is given. So using diffusivity and all heat transfer data, I can calculate the mass transfer coefficient, and hence I can calculate the rate of mass transfer.
Sir, Kc value is 0.105 meter per second.
Okay, 0.01105 meter per second. Okay. Now Kc, what is the value of CAW?
So CaW value is 2.19 into 10 per minus 3 kilomole per meter cube.
Very good. This telling unit along with magnitude is the only correct habit of explaining any parameter value. Okay. So as Shashank has told, so it is with unit. Otherwise, Kc equals to 0.015 doesn't have any meaning. Kc equals to 0.01105 meter per second. Similarly, CAW. Now you can calculate CAW. CAW equals to, this is the appropriate value of R you can use. This pressure is used in bar. So you take the unit of R accordingly, and this is temperature is in Kelvin. So this is 2.19 into 10 raised to minus 3 kilomole per meter cube, and this is the rate of mass transfer. So one answer is this: estimate mass transfer coefficient and estimate rate of mass transfer. Rate of mass transfer is 3.45 into 10 raised to minus 4 kilomole per second. Everybody is getting this answer? Roll number 5, Aditya.
Yes, sir, I got that.
Okay, very good. So now here you can see heat transfer data was given. Heat transfer data was given means this heat transfer coefficient was given, and some related property in mass transfer is given, like DAB. DAB was the only property in mass transfer which is given, that too at 318 Kelvin. So we got the mass transfer coefficient for given case. This will give mass transfer coefficient which is equals to 0.105 meter per second. Once I got mass transfer coefficient, I can assume that bulk concentration of water in a air equals to 0. Okay, bulk concentration of water over air equals to 0, and then this will be area multiplied mass transfer coefficient, that will give you rate of mass transfer. Okay, this is clear to everybody how we can apply this analogy to solve the problem. Likewise, now here you can calculate what is the drag force exerted by flowing fluid on a what is that flowing fluid on a, so wetted surface. Okay. So what is the drag force exerted by flowing fluid on a wetted surface? Calculate drag force. Okay, drag force exerted by flowing fluid on a wetted surface. How to get that? Roll number 28, Lalitha. How to get the drag force exerted by flowing fluid on a surface? There is air and this is wetted surface. So how to get drag force exerted by flowing fluid on a surface?
Sir, we can use W equals to F into VCH.
W equals to
Drag force into characteristic velocity.
what is W?
Sir, it's power.
I'm asking what is drag force. I'm asking how to get FD.
Okay. Area into
Area into
K into F.
what is K into F?
Sir, K characteristic. I mean,
Characteristic kinetic energy. How to get characteristic kinetic energy?
half into rho into VCH square.
Okay. How to get then drag force? That shear stress tau W.
That half into rho into V square into F. Finning.
Thinning. So what is how to get that thinning? How to get thinning? Roll number 60, Aditya.
Yes, sir.
How to get finding friction factor?
Sir, we can average it over the area of the plate. Like,
Okay. So how you
uh,
are going to average? Local value of friction factor is given.
uh, no, sir, it is given for uh, overall area. Sir, drag force is calculated by if you know the area of the surface, then area
You
of
know the
surface.
area actually.
Yeah.
So
Uh,
how to get a wall flux tau W shear stress at the wall?
uh,
Shear stress of the wall can be obtained by using Fining equation.
yes,
How
sir.
to get Fining friction factor?
Uh, so just a minute.
Yeah, Prashik, roll number 79.
Sir, uh, we can find the friction factor if we know the type of flow, like laminar flow or turbulent flow. Uh,
Okay. So given data
if
is
the
not enough.
uh,
First of all, Prashik, why you are written name like this? This I told you, na?
Yes, sir, sir. My laptop is not working properly. That's why I joined from a mobile phone. So it was this one was the default one.
You change the default one then while logging
Yes, sir.
in.
I'll change it. Yes, sir. I'll change it right away.
Yeah, tell me who was telling that how to get finding friction factor. Anybody else in a
uh,
class?
Sir, using the Chilton-Colburn analogy.
Very good. Roll number, your roll number, please.
Sir, 111.
111. So using Chilton-Colburn analogy, so for flow over a flat plate, okay, this is wetter surface. Okay, this is flow over a flat plate. So F by 2 equals to JH,
Yes, sir.
and JH equals to standard number
JH.
for heat transfer into Prandtl number raised to 2 by 3. So you
Yes, sir.
can easily estimate friction factor. Okay, so this is what I am telling. So this only use this first part. For calculation of mass transfer, we have used this because heat transfer is defined. All the parameters in heat transfer is given properly. So using this second part, JH equals to JM, we got mass transfer coefficient. This calculation already we have done. Similarly, using this first F by 2 equals to JH, because this is true for flow or flat plate. F by 2 equals to JH equals to JM. So JH is, what is JH? JH is Stanton number for heat transfer into Prandtl number raised to 2 by 3. Stanton number is given, already given. So you can see H is given, rho is given, Cp is given, velocity is given. So you can calculate this. Prandtl number is given, that is equals to F by 2. So twice the multiplied by this, that will give you friction factor. Now using friction factor, you calculate shear stress at the wall using Finding equation. Okay, and multiplied by area, that will give you drag force. So what is the value of drag force? Here, roll number 111.
Sir, I'm calculating.
Okay, calculate drag. First of all, get me the value of friction factor. Yeah, anybody else got the value of friction factor? Yeah, roll number 72, Mithali.
Yes, sir. Sir, 1 minute. Do
1 minute will cost you a lot actually at the end. Roll number 25, Nivas. What is the value of friction factor? Huh? Talk loudly.
Calculating, sir.
Huh? How to calculate friction factor?
The standard number into Schmidt number 2 by 3.
Standard number into Schmidt number. Excellence, Nivas. Actually, you are into class properly. Roll number 1, Abhinav.
Sir, what are you asking?
What I am asking, what is your name?
Sir, I have calculated friction factor, but I thought that you are asking how to calculate.
Okay, you tell me how to calculate and what is the value. Both you tell them.
Sir, by using Chilton-Colburn analogy, we can calculate friction factor.
Okay.
Sir, we know Stanton number we can calculate, and we know Prandtl number. So from that we can get friction factor.
So what is the value of friction factor you got?
I got 0.0123.
0.0123.
Yes.
So anybody else got any other value? So what is the drag force? Roll number 38.
Yes, sir.
Drag force.
Yes, sir.
Calculating.
Sir, I'm calculating. Sir,
Very
I
good.
was
Very
able to
good.
calculate.
Keep on calculating throughout life.
Yes, sir.
Roll number 80, Shivani.
So just 1 minute, I'm calculating.
Yeah. This everything will be counted in your Viva of 20 marks. This you are calculating that everything will be counted because I know how long it will take. Because you people are not sitting with a calculator, you people are not sitting with a notebook, you people are not sitting with a pen in your hand. You are just listening like some storytelling is going on. This is not a storytelling. This is a transport phenomena. This difference you should understand. Roll number 70, Darshan. Darshan, roll number 70. Not audible. Roll number 49, Jayant. Roll number 49, Jayant.
Hello, sir.
Yeah, tell me.
Sir, I'm roll number 38. Sir, value of drag force will be equal to 2.0817 into 10 to the power minus 6 Newton.
What is unit?
Sir, Newton, no.
Newton. 0.
2.08 into 10 to the power minus 6.
10 power minus 6 Newton.
Yes, sir.
2.08 in power 10 power minus 6. Yeah, anybody else is getting this answer? You can write in chat box. Point. Oh, this is 28.427 Newton. Yeah, roll number 38, you got wrong answer, I think.
Sir,
I don't have
I'm check.
answers.
Sir,
So, you people are not even eligible to call as a student of VNIT as far as your performance is there. Na? So, nothing, this kind of behavior is not expected from you at 28 point something Newton. Many people are getting that answer 28.47, 28.5. Okay, 28.5 Newton is a drag force. Yeah, very good. Many people are getting. So roll number 38, you are wrong somewhere. Okay. So this is how we can use a analogy, and there are thousands of analogy available. So what is main aim of analogy is if data is given in one area, say data was given in heat transfer. Data was given in heat transfer, and we have done a calculation in mass transfer and momentum transfer. We are able to calculate drag force. We are able to calculate shear stress. This is the design important parameters in momentum transfer. Similarly, we are able to calculate mass transfer coefficient. We are able to calculate rate of mass transfer. This is the design important parameter in mass transfer. So these are important parameters. So we can do the calculation in one area with a given data in another area. That is what analogy will be used. Where analogy will be used. Now this you can calculate. Okay, this is actually interface flux. Okay, Newton's law of cooling. So that we have not done a problem solving on that. Okay, Newton's law of cooling. So now we will do that. Okay. So take out all the given data and solve this problem. Air at 20 degrees Celsius flow over a flat plate. Area is given 50 by 25 centimeter. If average heat transfer coefficient is given, determine the steady rate of heat transfer. Rate of heat transfer from one side of the plate. If plate to the air, from plate to the air, if plate is maintained at 40 degrees Celsius, plate is at 40 degrees Celsius, so void temperature is 40 degrees Celsius, bulk temperature is 20 degrees Celsius, surface area is, so rate is, you need to calculate rate, so area is not needed at all, rate of heat transfer. So only heat transfer coefficient multiplied by delta T, that will give you watt multiplied by area. So rate will be area H A delta T. Flux will be H into delta T. So This is simple. Just put the values and get the answer. Roll number 64, Shubham.
Yes, sir.
So what is the value? Rate of heat transfer. And calculator.
Yes, sir.
Yeah, very good. Yeah. Calculator is there with you. Very good, very good, very good. So what is the answer to this problem?
So I'm getting 625 watt.
Yes, sir.
Yeah, very good.
625 watt.
Correct, correct. So very easy. H into area. Here only you convert that area into area. This is centimeter square. 15 to 25. You multiply by 0.5 into 0.25. That's all. 250 multiplied by 0.5 multiplied by 0.25 multiplied by 20. You will get 625. Is it so, na? Correct, na?
Yes, sir.
Okay. Now air at 15 degrees Celsius flows over spherical tank of LPG tank 4-meter radius. So outside the temperature of the tank is 4 degrees Celsius. So wall temperature is given, bulk temperature is given, and rate of heat transfer is given. Now what will be the area of spherical? What will be the area considered here? First of all, surface area of, for heat transfer. Roll number 62, Rameshri.
Sir.
What will be the area? LPG spherical tank. Area for heat transfer, area available for heat transfer.
Surface area over there.
Yeah,
4
what
pi
is
r
surface
square.
area? How to get surface area? Radius is 4 meter.
4 pi r square.
Yeah?
4 pi r square, sir.
4 pi r square. So 4 pi r square multiplied by delta T multiplied by H, that is equals to 62,000. So determine heat transfer coefficient. So what is the heat transfer coefficient, Rameshri?
Or I'm calculating. Sir, 250.
Yeah?
250.
250. What is unit? I told you, na. You should tell unit also. Heat transfer coefficient is not a dimensionless number. What is the unit of heat transfer coefficient?
Watt per meter square Kelvin.
Watts per meter square Kelvin actually. What the value you got?
250.
250. Answer is 28. So how come you are making anybody else is
Sir,
getting this
you said
answer?
heat transfer coefficient.
Huh?
It is given one is 250, sir.
Heat transfer coefficient is given. Determine the average heat transfer coefficient. Which problem you are talking about? Still you are here?
Sir.
Huh?
No.
So still you are talking about,
So
say,
62,000 equal to 4 into 4 pi r square h into delta t. H is 28, sir. Yes, sir.
so here people are solving 3.3 problem and you are still on 2.2.
Sir, it is written in the. So now I'm saying 62,000 watts equal to 4 into pi r square into delta t into h, and 62,000 by this one we'll get h. H will be 28.0 watt
Okay.
per meter square Kelvin.
Anybody else getting any other answer?